So this is my final exam validation video, and I'll be going over items 1, 3, 5, 7, and 9. So let's begin. Item 1 gives us a table of values. You have the position of a cyclist D, and then after T seconds, which is at this table. Then for A, it asks for the average velocity for each of these given time intervals using approaches introduced in Chapter 2. Well, in Chapter 2, we know that the average rate of change can give us, the average rate of change, the change of a function over an interval of some quantity. It could be time, amount of earth excavated from a hole or a mine, anything like that. It's always to an independent variable. In this case, velocity is the rate of change of position over time. So this would be delta D over T. So for the interval 1 to 2, it would be 24 minus 10 over 2 minus 1. Then for 2 to 3, it would be 42 minus 24 over 3 minus 2, and so on and so forth for the final interval. Then for B, it asks for an estimation of the cyclist's instantaneous velocity after 2 and after 3 seconds, which means actually at 2 and at 3 seconds. So we want an estimation of V2 and V3. We don't have a derivative function, but we do have the table. We know from our definition of the derivative graphically that you have a graph, some function here. You have a secant line, PQ, point P, point Q, with their respective points. And the idea with the limit, with the derivative, is that you let Q get closer and closer to P. That secant line gets closer and closer to point P, point of tangency. You zoom in, that point of tangency and the graph become essentially the same. So that's the idea of limits with the derivative. So we can use that same idea here. For the instantaneous velocity at 2 and at 3, we can just take the slope, delta D over delta T for those times. But the difference is that it would be for values slightly larger than and slightly lesser than, but close to their respective position and times. So for 2 and 3, you can actually see that work down here, where I use that estimation method with the idea of limits. See that down here as well. Then for part C, it asks for the best fit curve for the position function. The position function would be S of t, or D of t in this case, actually, which we have. So yeah, that would be D of t. Graph the table of values of Desmos. Go down here, you can see that graph. Then for parts D and E, it asks, based on the given data, determine if the cyclist's velocity is constantly increasing. Based visually, we can see that it is. Then we can also go down to our calculations, to see that it is increasing as well. Here's the average velocity for the data table. You can see that there's a general increase. So numerically, it's correct that the velocity is increasing. Now for part E, we want to know, based on the best fit curve, is it increasing? Best fit curve, we go down here, we can see that the slope of this line is positive. It's tending towards an increase. The velocity is increasing here as well. Then for F, it just asks for a comparison and a contrast of the analyses and the two resulting outcomes from part D and E. Well, from part D and E, we got the same outcome, which was that the velocity was increasing. The difference was that the methods we used to get there. D was with the table and those calculations for analytical proof, and then E was graphical. The similarities between the two methods is that it's based upon finding the average velocity, which you can do with the average rate of change, slope from algebra. Yeah, that's the similarity that they have. And also that it could tie into the idea of limits if you wanted an extremely precise measurement. because in mathematics, when you take an idea and you go further with it, you repeat it, you can get extremely precise measurements. But we can't do that in the real world. We can only approximate. But in math, we can get as precise as we want. So now that item 1 is done, I will move on to item 3. Item 3 asks for the definition of the derivative function value f prime of a. F prime of a is the derivative, is the definite, f prime of a is the derivative of a function at a specific number on the original function. And so that definition is the limit as h approaches 0 of f of a plus h minus f of a over h. And that's important because a is the number that is being approached by h. A could be 5, it could be 10, it could be pi, it could be e, any number. Key thing to focus on is that it represents a derivative on the original graph of y equals f of x at a specific number, where x on the original graph is actually your a value. So a equals 5, that would be the derivative of the slope of the tangent line at that point of the original graph. And then for b, it says that each of the following limits represent the derivative function value f prime of a. Then you want the function formula for f prime of x and the value of the input a for each case. For b1, this limit is of the form f of x minus f of a over x minus a. Now, if we look at the denominator here, x minus a, you can see that a equals 1. You can see that visually, and that just ties into knowing the definitions, the formulas for the definition of the derivative, just knowing which part corresponds to your problem. So here, a is 1. Then over here, we have f of a. So that means that f of a must be, we have f of a is 2. So f at a, or f at 1, must give the value of 2 here. And another thing to note is that f of a, in terms of a function, is just whatever f of x is rewritten in terms of a. And we have f of x here, which is 2x. So visually, 2a, f of a is just 2 to the a power. So we plug in a, 2 to the first power, that gives us 2. That's a quick way to confirm that a is correct and that the function formula, f of x, is correct as well. And it's a similar process for the second one over here. You have the popular, the first definition of the derivative at a point, f of a plus h minus f of a over h. Yeah. And so here we have this part, f of a plus h, based on this portion here, and what we talked about previously with the other problem, a is equal to 3. So we have also here that f of a is equal to 9. And we have that a is 3. So if that's true, then f of a must equal 9. And f of 3 must equal 9. Well, what's f of x's function? Because again, if we have f of x, we can get f of a. Well, we know that f of x plus h, we know that f of a plus h is equal to 3 plus h. Actually, this one is a little bit more involved, so I'll go down and show my work, just so you know where I'm getting this from. So for 2, again, like I said, f of a equals 9 and a equals 3, so f of 3 must equal a, which is 9. So we have here, basically, a is 3 and f of a plus h is, that turns into 3 plus h squared. And, you have f of 3 plus h equals 3 plus h squared. So you want f of x, that's just a substitution at this point, which turns into f of x equals x squared. Because we have that, f of a is a squared, and that comes out to be 3 squared is 9, which proves the original problem. Now for the second part, it says that we have limits that represent the function value f prime of x. Well, actually, the first part, it asks for the definition of the derivative function f prime of x. That's the limit as h approaches 0 of f of x plus h minus f of x over h. That's just the derivative as a function for all values of x on the original function y equals f of x. The slopes of those tangent lines and all of them added together. So for D, we want f prime of x and the function formula. Well, we want the function formula f of x for each case. Again, this just depends on you recognizing the definition of the limit and knowing what part corresponds to the definition. F of x is the function subtracted from f of x plus h. So for D1, it would be x plus 1 raised to the 3/2 power. Then for 2, it will be sine of pi x. And that's that for that section. Then for E, it asks for a comparison and contrast of the significance of the derivative as a derivative function value, as well as a derivative function. Well, the comparison is that they both have to do with derivatives. That's the point of them. The difference is that one is the derivative as a function, so a general function for all inputs on the original graph, and the other is the derivative, or the tangent line, at a specific number, a, on the original graph. So if a is 5 for y equals f of x, and you want the tangent line, you would just use the second definition and swap out x with a to explain that. Now I'll move on to item 5. Oh, and before I forget, here's my work for item 3. The proof of what I was talking about. All right, now we will go on to item 5. So the problem says that the problem has to do with changing related rates. So we're given that as a spherical raindrop evaporates, its volume changes at a rate proportional to its surface area. And we have A. We want to find A first. Well, let's look at the problem. We want to prove that the rate of change of the volume is proportional to its surface area. That's just, we want to prove dV dt is proportional to K, constant times the surface area. That's how we get that formula. And then if you want to prove that through, well, the volume of a sphere is 4/3 pi r squared. Pi r cubed, sorry, 4/3 pi r cubed. So you can differentiate that to get this relationship here, the factor of dr dt. And then this is interesting here because this part here, the 4 pi r squared, is the formula for the surface area. So recognizing that, you can substitute that for the surface area to get this relationship. dV dt is equal to the surface area times dr dt. Then you want to go back to proving the proportionality between the two. You can just set the equations equal to each other and do some slight manipulations, which are shown here for convenience. After some substitutions and a little bit of algebraic manipulation here, the surface area as a variable, a term to mess with, we get that the negative proportionality constant A is equal to dr dt, which shows the problem statement that we were first given. Then for part A, it asks the constant of proportionality is K to find the rate of change when the radius is 4. Well, we can't use that with the volume formula because that has its dr dt, but it just wouldn't work with the volume formula. So you want to take the surface area formula, plug in r for 4 in order to get a value here, and then substitute that back into dV dt to get the surface area times dr dt, but with a value. You could also manipulate that for dr dt to get its reciprocal, which is still a numerical value. So we couldn't exactly find a numerical value for the rate of change of the radius, but we know that it's a number of some sort if we were given dV dt. But the greater idea is just to show that the rate of change of the volume and the rate of change of the radius are related. So for part B, it asks that the rate of change of the radius is always constant. So that means if you imagine a spherical raindrop evaporating, that the change of the volume is constant. well, the change of the radius, this, if you have a circle here. I want to show that the rate of change of the radius is always constant. The way I approached this was just taking the relationship we had before and then solving it for dr dt, which is the only way I could think about it. So for me, this shows that dr dt is constant because it has a numerical value. There's a relationship here. That's how I reasoned it out. And for part C, does part B mean that the rate of change of the volume is always constant? Why or why not? Explain your answer. The rate of the change is the rate of the change of the volume constant. It has to be, since the rate of change of the volume is supposed to be related to the rate of change of the radius. If they're related, then they do have to be changing constantly with respect to each other and time. And again, you can show that algebraically, symbolically with the relationship up here, but just solving for dv dt, and then there's the proof for that. Then for the explanation, yeah, I explained it. So we have that. And then for the reflection, my skill takeaway was just, being able to do some related rates problems, learning to differentiate equations with respect to another variable. I needed a refresher on this topic. And also my knowledge takeaway for this problem was you don't always get a number when you're solving a problem. You get a symbolic answer, and that's okay. Because with those problems, they want you to focus on the relationship between two quantities or two equations and what they're trying to describe. So now I will move on to, now that I'm finished here, I will move on to item 7. So the problem is a waste-free box. You want to make an open-topped box. Here we can see this. Now for A, what is the maximum possible combined volume of an open-topped box plus a pencil holder that can be made by cutting 4 squares from the 8.5 times 11-inch sheet of paper? Describe the open-topped box that gets the results from the maximal case in part A. Intuitively explain when we get the result we do. You want to declare your variables first. And we'll go to my solution. I'll explain it along the way. Here's a handy drawing of the box. We get these dimensions here because, and this is an optimization problem, we have here the 4 rectangles of equal lengths and widths in terms of area, x and x here. And so when we cut those corners away, they're going to be reused, but we're folding up this box. So the x's along here, since this x is the same as this x, this becomes 8.5 minus the change in 2x to account for that when it's folding up. And it's the same for here with the 11 minus 2x. That's how we get those lengths, those expressions for the width and the length. And for the volume formula, that's length times width times height, cubed and all that. So we get that extra x here by accounting for this side here. So that's how we have our volume formula. And then you want to find the maximum volume possible. So this gets into the critical numbers test. So the first thing is you want to solve for x and find out the x values. So we get that here. And then you want to sub those back into the expressions to see what they give you. This is going to determine your domain for your value. The lowest you can get is just x is less than 0, less than or equal to 0, which basically gives you the box you started with. But for the highest one, you want to play around with those values and see what it gives you. Here we've done that, and you can see that negative values are excluded, in that you cannot have a box whose dimensions have a negative component. That's not a part of the real world. Dimensions are positive. So we want the x value that gives a positive output. We have that here. So the domain of our maximum volume for this box is x is between 0 and 4.25. No, yeah, 4.25, inclusive of those points. Here I have a little explanation here for that part. Now that we have our domain, we want to find the largest possible volume. We want to take the derivative of our volume function and then set it either equal to 0 or where it's undefined, because doing that to the derivative and solving it for x is where you find the critical numbers. And then remember the critical numbers, they're a potential candidate for absolute max or mins, which is what we're looking for in optimization problems. So we have that here. We have the derivative down here. And then you want to find critical numbers by solving this for x. This trinomial doesn't factor nicely, so I had to use a quadratic formula to get these values, which these are their approximations to make calculations easier. This one, which is the first one here, x is equal to the negative 78 plus square root of that rest, it doesn't work because it's outside of our domain. 4.9 is greater than 4.25, so that value doesn't work. This only leaves us with the second option, which is this, or approximately 1.585. So we can plug that into our volume here. And we evaluate this. Oh, yeah, our critical numbers. This is our critical number that works. So now we want to test it to see if it gives us absolute max or min. So we evaluate it at our endpoints. That's 0 and 1.85, no, 1.585. We evaluate that here to get, let me see, go down here. We evaluate this. Oh, I'm sorry, yes. The endpoints, you want to evaluate it at 0, and then our upper boundary, 4.25, and then as well as at the critical numbers. And compare. Here we can see that V at our critical number, potential one, is the highest. So this means that the maximum volume of our box is approximately 66.4 inches cubed, because units were in inches. Then for part B, it asks for an intuitive explanation of the open-topped box, the result from the maximum case, part A. Well, it's a box that has a volume. The only difference is just it doesn't have a floor. It doesn't have a bottom. This is still a three-dimensional figure, so it has a volume. And you get that from folding up the cutout squares, like those cubes. You would fold up those sides to get that. And again, like I explained, since the squares are equal dimensions on either side, the overall rectangle, those dimensions switch from 8.5 with the x's to the 11.5 of the x's. It becomes 8.5 minus 2x and then 11 minus 2x. And you can see that visually when you fold up the corners to get that box. Intuitively, that's how you get it. Now, here's my work as well. You can see it, the explanation. And now finally, I will move on to, before I do, my reflection. My idea takeaway was just the importance of critical numbers and how they help you solve optimization problems. Because optimization, you want to optimize something, get it the best possible way you can. Like if you're looking for the smallest value of a quantity or the largest, that's the idea. And critical numbers and derivatives, that whole test, it's very important to optimization. So my idea was just seeing how they're related and how the steps, they're important. They're not just for nothing. Has a purpose. Then for my skill problem, it was my skill takeaway, it was refining the derivative process, getting good at doing that algebraically, and then practicing other algebraic concepts like the quadratic formula. It's been a while since I've done that one. So that's my reflection on that. Finally, I will move on to item 9. And this just asks us to integrate these to determine the antiderivative functions. We have this function here. So for number 1, this is product of one variable and then another function. This would require u substitution, or just variable substitution. EU, where u is x squared, du is 2x, which would give you the integral of x e to the u dx. But you want to substitute, you want to find a substitution that takes care of the x and the dx. So du is 2x dx. Du would be, 2x dx. Du would be well, actually, no, dx. You want to get dx because that'll give you du where you substitute. So dx would be du over 2x, which is 1/2 over dux. You can see that integration over here, how that actually helps you cancel out the x and the x here. So that worked out really nicely. That gives us this, which you integrate, that's the constant times the e to the u plus c, but you always want to back substitute with x because you want that in terms of x. And you get, this is actually supposed to be 1/2 e to the x, well, e to the x squared plus c. I made a mistake here. But that's what it would be when you'd substitute it back in. Now for number 2, this is a product of a variable and a function. This would require integration by parts, which is the integral of u dv equals uv minus the integral of v du. And this undoes the product rule, calls back to the relationship between derivatives and integrals. And so your first step, you want to choose u. Now there's a helpful acronym that helps you memorize this, but I didn't really memorize it. I just memorized the functions, I guess, in order of importance. SLIPT or Liate, which is logarithmic, inverse trig, polynomial, which is power or any other sort of algebraic function, trigonometric, and then exponential. Based on this, we have x to the first power. So that is high in the pecking order, takes priority. This is our x. No, this is our u. Yeah. So u is x, du is dx, which is really nice. It works out. Then what's left becomes dv and v. And this is important because you want the integral to be, at worst, the same level of difficulty as the one you started with, or easier. So that's why you really want to know what you're doing when you choose u. So again, dv would be e to the x because that's what's left. And then v is just the integration of that, and that's e to the x. So we can sub this in for our integration by parts formula. X times e to the x minus the integral of e to the x dx. You integrate that, that's x to the ex, x times ex minus e to the x plus c. And then for b, it asks us for a general strategy to integrate a function to find an antiderivative. Then for c, compare and contrast the integration techniques we use to determine the two antiderivatives. For b, it just depends on the way the function looks. Like if it's a complex function where you have 1 plus x squared that you know you have to use substitution, that's where you use substitution. But if it's a product of two functions like x squared times 5x plus 3, that's where you use IBP, integration by parts. As for the comparison, they're both similar in that they deal with integration. The contrast is that their methods differ. One is just substitution, which is simple. It undoes the chain rule. Whereas for another one, you're dealing with a complex integrand where you have the product of two integral functions like I described a few seconds ago, which in that case you would use IBP. You can see my work here for both. Then for my reflection, my idea was getting a refreshing part of integration by parts and just how it relates to the product rule. Just getting a deeper understanding of that relationship. That was the takeaway for me. Then as for my skills, it was catching up on integration techniques and getting practicing. Because prior to this point, I had been focusing on the current topic, and so I didn't have time to practice integration by parts or integration by substitution. So yeah, and that's my reflection. Now, before I close this video, let me just go back and do the reflections for items 1 and 3 and 5. So for 1, my reflection was just, again, getting comfortable with the average rate of change and how it can model changes in the real world between items or forces. My skill takeaway was using estimation because prior to that, I hadn't done estimation in a long time. And in math classes, everyone is so concerned with getting the right answer, even with estimation. It's like, no, estimation is an estimation. It's not meant to be perfect. It's meant to be an educated analytical guess. So that was my skill takeaway. And also how estimation can be used to approximate the derivative numerically, like a value. Then for item 3, for my reflection, my idea of takeaway was just knowing the definition of the derivative function and realizing that, that's where our derivative rules come from. And also my skill takeaway was being able to perform some slight algebraic manipulation and finding these functions and their values by recognizing some properties like I described in the problem originally. And also my idea takeaway was just, being comfortable enough with the definition to where if they throw something at you, you can use some intuition to solve the problem. So that's my validation video. Have a nice day.